Hey Jenna, okay, let me get it started and we will begin. I know the others are coming in, so let me give them a little time. Okay, what's up? Let's get to it. So I will just start the actual review on each one of them. So I'm gonna have the little Word document here to the side and, oh, what's up, Fady? Okay, I'm gonna minimize this and I'm just gonna be going through each of the op amps. Then we can do a few questions after on the actual assignment. And so here we go. For the op amps handout, so we'll just start with all the basic op amps. We see the first one, which is open loop. So there's a difference between open loop and closed loop. So open loop is basically no feedback. So if you look here, there's no feedback. And by what I mean by that is there's no connection to this negative terminal here. And so you can see in the closed loop here, we have a connection to the negative terminal here, here. And then if we scroll down, we have another connection here to the negative terminal and they're here. So that's what our closed loop versus open loop means. So when we have it here, we can say open loop, no feedback, where this is feedback to the negative terminal of the op amp. So now we know the difference between the two. So for voltage comparator, for zero crossing detector, we set V reference equal to 0. So what does that mean? So I'm going to give you guys a little bit of an example so you know what zero crossing means. And so let's say we have our graph here and I'm going to give some V reference equal to 0 like it said, so 0 volts here. And I'm going to make VI equal 2 volts peak to peak. So 2 volts peak to peak. And when I do that, it can be at like a certain frequency. And so let's just say the frequency makes the period 1 second. And so if I have 1 second here, and so this is time in seconds, and I have voltage along my y-axis here. I know for my V reference here, so I'm going to do that in red, it's going to stay at 0 volts. So 0 volts here for V reference, and I'm going to label that one. While the other one is going to be our actual V in. And so V in is 2 volts peak to peak. And so I'm going to show you guys, if it's 2 volts peak to peak, that means 1 volt amplitude. So you guys know. So right here, and the period is every second. I just made up. So we have 1 volt positively, 1 volt negatively. And we're going to see V reference. We have a zero crossing detector here, because what that means is right here at the 0 point and here at the 0 point, and then right here, it's going to cross. You can see the two intersect. And at that point where it intersects, you're going to tell there's going to be a change in the output voltage. And so when V reference is greater than VI here, so I'm going to do a little equation here. So V reference is greater than VI. We can see we're going to get a positive number in on the side of the equation. But if we get V reference is less than VI, so if VI is bigger than V reference, then we're going to get a negative number. And so you guys know, that's how you look at this side of the equation. And the output will be reflective of that certain change. And within our open loops, so you guys know, a very important characteristic of this is the gain is infinite. Where here, the gain is finite in a closed loop. So here the gain is infinite. And how the gain is infinite, so you guys know why, is because we don't have any feedback here. So if you think about it, if there's no feedback happening, that's sort of like if you have infinite resistance here for your feedback resistor. So if you had an infinite resistor, that causes no current to come through. And that would be then an open circuit, you could sort of say it like, because there's no current able to pass through. And so that's why the gain is infinite in an open loop. versus in a closed loop, the gain is a finite number we see here where it's RF over RS, or it can be 1 plus RF over RS. And now that we went over that, I'm going to now go back to the open loop example here and show you what the output voltage would look like. And so we know for the open loop, the gain is infinite. So I'm going to write here just the infinity symbol. And one thing we know is the output voltage can only approach the maximum voltage supplied by ±1 volt. And so what that means is this output voltage, if I'm supplying 15 volts to the positive and 15 volts negatively to this amplifier, so that would look like this. They don't show it, but that's the typical. So negative 15 volts here. And if I put in plus 15 volts on the other side where the positive terminal is located, that means the output voltage can only approach the voltage supplied by plus or minus 14 volts, depending on the sign here. And so what we know is typically for an op amp, it can approach plus or minus 14 volts because the input voltage supplied the majority of the time is plus/minus 15 volts. Okay, now that we talked about that, let's look at our output voltage graph. So if we look at this specific portion right here, we see that we labeled in green the input voltage. So the input voltage is greater than the reference voltage. So we're going to get a negative number since this is a bigger number on this side than this one here. We're going to get a negative number multiplied by the gain, which is infinite in an open loop. So it's going to stay at negative 14 volts here. And then we notice what happens is at this portion where the input voltage is less than the reference voltage, that means that this number right here is going to be smaller than the reference voltage. So we're going to have a larger reference voltage since it's at 0 and the input voltage is below 0. So we're going to get a positive number on this side of the equation. And so since we have a positive number multiplied by infinity, that's going to approach the voltage supplied by 1 volt. So it's going to be 14 volts positively. And then it will be going between the two. We'll see because this green wave here will keep going through each period. And so it will keep changing the output voltage. It will go from negative 14 volts to positive 14 volts back to negative. And we'll see the resulting waveform here. It's going to sort of look like a square wave. And we'll see that as a result, this is what our output voltage will look like. So, you know, and with the square wave, one important factor to consider is that there's slew rate. And the slew rate is the time it takes for the output voltage to change. That was one thing Dr. Ari mentioned. So it's not a straight square wave as your output. It has a little bit of a slope to it, just a tiny slope. And that's because it takes a little time for the output to change as a response. So that's the effect that a slew rate will cause on it if he brings that up. And now that we talked about the open loop voltage comparator with zero crossing detector, let's talk about the one with regenerative feedback to give noise immunity. Okay, so for the next op amp, for this one, what we're going to be looking at is we can see it has feedback, but it's not to the negative terminal. So since feedback's not to the negative terminal, we know it's going to be open loop. So there's no feedback here to the negative terminal, if you want to be precise. And what happens is we get feedback to this positive terminal, but we have the voltage source hooked to this negative terminal here. And what we see is when we do the equation, it's exactly the same. You can see as written up here where V reference was connected to the positive terminal. And so that we can say VP here. And we can say VI was hooked up to the negative terminal here. So we can write VN here. So exact same part right here. And then what we do is we multiply it by the gain. And we notice here for VP, we can write it in terms of voltage division here. And so the reason we can write it in terms of voltage division is because think about this curve. So we have our RF here, and then we have our RS here, and then RS is hooked to ground, and we have our point VP. And so VP, we have our output voltage here. So VO being one of the points there. So let me just write it as VO, which is supplying the voltage because that's at the highest point. Because we're going to only look at this section right here. And so we know VO, and after it, we have RF and RS. So we have the feedback resistor and the source resistor. And we know VP, the voltage there would be the same to the voltage across this RS because it's at the same potential. And so if we want to find VP, we would set that equal to the voltage from the source, which in this case is VO. And then the resistor we're interested in, since VP is at the same potential for RS, we'd say RS over RS plus the other resistance in the circuit, which is RF. So RS plus RF, and that's how we would get this portion right here for VP. And that's what we can put into our equation. And so now that we know how to do voltage comparative with regenerated feedback, so why do we have this? I'm going to show you an example here so you can understand it. When we have noise, a lot of the time, so let's say we have a graph like this and looks something like this, and we have our signal here. Our signal here looks like this. So it's sort of like our sine wave we're used to seeing, but we can see it goes up and down, up and down, up and down, up and down. And if we have our reference voltage, which would be somewhere here and here, we're going to see it's going to be changing. So let's zoom in to the specific portion right here. We'll notice when we blow this up, so I have it right here and I have my green sine wave, it will go through and intersect it 1, 2, 3 times. If we just take a zoomed in portion, 3, oh, maybe 4 here. So we can see it intersects 4 times. So what we do with this is we give it noise immunity since we're able to change the reference position. So then if it intersects once here, then the reference would change and go down here. So it would stop intersecting. And then when it intersects this once, then we would change it down here. And so we change our reference point. And so that's what this voltage comparator basically does, is it gives noise immunity by changing the reference. And so that once it intersects it once, then it changes that reference position. Okay, now that we talked about those and know how those equations come into being, we're going to talk a little about the closed loop. And so the closed loop here, the main ones you guys need to know are the inverting amp, the non-inverting amp, and the follower. So the inverting amp, how I like to think about this one is we have a negative sign here, so it's going to flip it, so it inverts the output from the original input. The non-inverting amp, there's no negative because the output is positive, just like the input, whatever comes in, comes out in the same exact phase. And then here for the voltage input, for our follower, it's the exact same as the output. So those are the good ones to memorize. And so you guys know how these equations come into being. You can do the derivation of them where you actually do Kirchhoff's current law. So I'll show that for one of them, but after that, you can basically apply it to the rest. But I want to tell you guys how I memorize these. So for the inverting amp, I know it's the gain, and then we know from our equation, it's usually the gain times VP minus VN. And we know our gain here. It's going to be a finite number since we have our voltage feedback. It's RF in the other resistor we call RS. It's just an arbitrary name. There's nothing for the S, but F means feedback. S is just arbitrary. And so what we have here is it's negative RF over RS for our gain, since it's an inverting amp, and the negative sign is because it's hooked up to this negative terminal here. And what we do then is we multiply it by, if we look at VP here, think about it. VP is at this point, which is 0. So this will cancel to 0. VN is at this point, and VN, we see there's a voltage source. And so we have VI here. So that's where VI comes from. And then the gain is RF over RS. So this negative sign, because VN, we can write it as, let me just show you guys. We know the gain. We have our feedback resistor over the other resistor, which we call RS, times, and then we have 0 minus VN. In VN, we can tell the voltage coming in, it's going to have this voltage source, and there's going to be some voltage drop across RS, but it's so minimal due to the input bias current. So for this, we can just say negative VI. And that's how we get the equation here, is it's just the negative sign in front, and then they do the gain times the voltage VI, which I technically can say is almost close to VN, because our bias currents are so low. If you look from the actual data sheet here, the bias current coming in for each of these is right here. It says for our bias current, let me show you, it's 80 nanoamps typically. And so when we do 80 nanoamps, that's times 10 to the negative 9. So times 10 to the negative 9 times a resistor here. Sometimes it's so minute, it doesn't even make a difference. So we have, so you guys know coming through is 80 nanoamps of input bias current. Okay, for the analog inverter here, what we do is the analog inverter, the difference it has is the resistor, the other one is exactly the same as the feedback resistor. So this equation here, RF over RS becomes RF over RS, because RS is RF, they're exactly the same. And so it just becomes negative VI. So it's basically just throwing in that we know RS is equal to RF in this one. And that gives you the negative VI. The inverting summer, this one is different, but it is not that hard, trust me. Basically, just forget about these down here and just think of the RA and VA. If you think about that, it's just a regular inverting amp, because the voltage is on the negative terminal, and we have feedback to the negative terminal of the op amp. And so if you think about that, it's just negative RF over the other resistor, which is RA, times the voltage coming into that negative terminal, which is VA. And so that's exactly the same here. And what we do for the next ones is we just add the one for RB. So forget about this one here. And then forget about this one here. And that's how we get this portion right here. And then if we do the same thing where we forget about the other two and just do the third, we get basically this other equation down here, which is the RF over RC times VC. And so that's how we get the inverting summer. The reason it's called summer is because it sums up the A, the B, and the C portion here. And so it's the combination of all three, and it's an inverting amp. So that's where the inverting comes from. And then number 6, which is the non-inverting amp, you can see right here, the difference is that we keep the output the same as the input. So they go in the same direction. But the difference is that we have 1 plus the RF over RS times the voltage coming in. And so that's what we have. And we can see the voltage coming in here is hooked to the positive terminal. And the reason why it would be non-inverting, if you think about the original equation where we had gain times VP minus VN, we know VP will be greater than VN since VN is hooked up to 0 volts here at ground, but VP is hooked up to this voltage source here. So this will produce a positive number, and a positive number times the gain is going to result in a positive number because gain will be positive. And so that's for a non-inverting amp, is just so you know, its voltage source is hooked up to the positive terminal. And so that causes it not to become an inverting amp. And then
hold on.
Yeah.
So sorry. So the non-inverting amp is pretty much an inverting amp, but with a voltage source at the positive terminal.
Yeah, and then there's a ground at the negative terminal compared to the inverting amp where the ground's at the positive terminal and the voltage source is at the negative terminal.
God, because sometimes like out there for these problems, sometimes there's voltage sources at both, and I'm like, okay, what the fuck is going on? Like, which one is it?
Yeah, I'll show you how to analyze those. Those get a little confusing. And then we have the follower here, which the follower is basically the output voltage is equal to the input voltage here, because there's no, our gain is just 1 if we look at it here. And so basically all you need to know is the follower, it just has it connected back to the negative terminal and the voltage just hooked up to the positive terminal. So that's why there's no negative sign here. And so those are all the basic ones you need to know. And if you want to derive one of them, I'll just do the actual inverting amp one because that one's probably our best one. And then you can derive the others from it because he might ask you a question on that. And so we can say the current here is IS coming in from this voltage source. The current coming back from the output is going to be IF because that's the feedback current. And the current we can say going through I of N here because that's going for the negative terminal. And so we can write a Kirchhoff's current law at this node. So we have I of S coming in plus I of F coming in minus I of N because that's going out of it. And then set it equal to 0 because anything entering a node is equal to anything leaving a node. And so then what we do here is we know I of N, it's 80 nanoamps because that's the input bias current. So it's so small because that's times 10 to the negative 9 that we can make this 0. And so as a result, this equation where you can write I of S is equal to negative I of F. And what we now can do is we can write voltage divided by resistance gives us current, we know. So for I of S, we know it starts at VI and it goes to this point, which we'll call VN because it's the potential at the negative terminal. So we can write VI minus VN all over the resistance, which is RS here for that specific spot, is equal to negative and then multiplied by, if we look IF, it starts at VO and goes to VN. So starts at VO minus VN. And then all over resistor here is RF. Oops. And then what we do here is we solve. And when we solve here, we're going to want to get equation for VO. And when we plug it in here, so let's just start looking at anything we can possibly replace. And what we know is in a closed loop, there's a special rule you guys need to memorize. In a closed loop, the voltage at VP is equal to the voltage at VN. And that's only for closed loops, so you guys know. So that's a big major point. And we're going to apply that right here. And so what happens is at VN, we say that's equal to VP. And so if we know VN's equal to VP, then VP is hooked to 0 volts right here to ground. And so what I can do here is I can make this 0 and I can make this 0. And then I know VI over RS is equal to negative V out over RF And then let's look to solve for V out. I would multiply RF on the other side and take that negative sign with it. So it would be negative RF over RS times VN. So then I have my VI here. And if we look here, that matches up with our equation here. So if you know how to derive that, all you need to do is you need to write a Kirchhoff's current law here for the node with the feedback and the source. And basically you need to know the input bias current so small, you can neglect it. So that's why we made it 0 here. And in a closed loop, VP is equal to VN. And so that's why we knew VP is at 0 volts. So we could cross out VN here and solve for the output voltage to get your equation. And that's how you derive it. And so now that we know that and we know how to do it, I'll be going through the last 3 which he wanted us to know. So for offset voltage, bias current, and correcting DC errors. And then I'll go back to homework questions. I'll just solve ones if you guys want, which ones I know how to do. And so let's go through the op amp DC errors. And so for offset voltage, so voltage offset, what we need to take into account here is if VI equals 0, then we should think, oh, if our input voltage is equal to 0, and using the equation we know for a non-inverting op amp, if VI is 0 here, shouldn't the output voltage be 0 ideally? It should. But for a real op amp with the input voltage equals 0, we know we're going to have some offset voltage here because we know the voltage can fluctuate a little. So a lot of the times it's like they give us plus minus 5 millivolts or something like that. And so what you have to do is if they say your voltage source supplies 0 volts, so like they'll usually say the voltage generated is 0 volts. However, the voltage offset is 5 millivolts. And if you know the voltage offset is 5 millivolts, that means it can go in the positive or negative direction by 5 millivolts here. And so then you just plug in 5 millivolts here. So you plug in your plus minus 5 millivolts in whatever values you have for this, the resistor. So it'd be 1 plus your RF over RS. And that's what you would do. And your output voltage would be from plus minus whatever this value is here multiplied by the gain. And then for the next one, we're going to have bias current. So a lot of the times the bias current, what we can see here is we have our normal non-inverting amp because we have the voltage source connected to the positive and we have a feedback to the negative terminal. And so this would be our equation we would use for a non-inverting amp. And if our voltage generated, so the voltage coming into the positive source is 0 and the voltage offset is 0, then we should definitely have 0 in this equation because if there's no offset voltage, which we would write with this equation, exact same, just have the offset voltage and then plus RF over RS. So if this one, if we say we have 0 volts for VG and we have 0 offsetting, ideally, that would cause the output voltage here to be 0. But what happens is basically for a real op amp with VG equals 0 and VOS equals 0, there can be some input bias current. And input bias current is the current that flows through into the terminals of the op amp. And so VO equals, and then we have the same gain equation here. So this is our same gain. And this right here, look, it's I times R, guys. That's VP minus VN. Exactly the same. So that equation here, you can just rewrite as VP minus VN. And if you look at it, VP here, if we had, what's happening is it's IP times RG, since we said our voltage generated is 0 volts here. So the only voltage would be this input bias current times this source resistor, and then minus IN, which is the input bias current coming in here. And since we have 0 volts, we say ideally at the output. So let me draw that out for you. So if we had 0 volts connected to RS, as we can see right here, it's connected to the ground. So RS is connected to 0. And we also have RF connected to 0. So I'm just going to have RF here. And we say the output should ideally be 0. So we have RF be equal to 0. Then we can say these two, they both share 0 volts. So technically you could draw this as right here, these two in parallel and both connected to 0 volts. And that would cause these two, then we can say are in parallel since they're both connected to 0 volts on one side and both connected in the middle here. And so that's where we can write RS is parallel to RF and then times the negative, times the current, which is IN. And we know it's with op amps, it's the gain multiplied by VP minus VN. And that's how we could get it here. And so we just substitute in for VP. We know the current coming through for the input bias current to the positive terminal times the resistor by the source. And then the other one is the input coming into the negative terminal times the parallel combination of RS and RF. Okay, now that we talked about that, correcting DC errors takes all of these into account. So just think of correcting DC errors. It takes into account the non-inverting amp, offset voltage, and bias current. So this is what you need to analyze for each circuit you're given. So this right here, this equation, I will mark it. These have 3 different ones. So we have this, this, and this part right here. Okay, so the one in purple here, that one is going to be for a regular non-inverting amp. Where the one in pink here, that one's going to be for your offset voltage. And the one in orange here is going to be for your bias current equations. So that takes into account all the possible errors that you can get. And so what happens is he says right here is to limit the amount of errors you can get read due to this offset voltage and due to the input bias current when VG is 0. So these two right here are the ones that would cause errors within your readings, is this offset voltage and this input bias current. If you set VG equals 0, so we have no non-inverting amp right here, these two will produce the errors. So we adjust this 10K potentiometer. So we know potentiometer, what it does is it can go from 0 to 10K basically here. That's what we know. So you can set any resistance value. And so you adjust that resistor until the output voltage is 0 ideally, because when 0 volts is supplied, there should be 0 volts coming out because nothing's getting amplified. So that's ideally. So that's when we adjust the 10K potentiometer here until we get 0 volts for this output voltage when VG is 0. So then that takes away these two errors. And so that's how we get the correcting DC errors. And now I'm going to talk a little about the common mode rejection ratio, because that one was a little confusing. And so, you know, for the common mode rejection ratio, that's basically, he likes to abbreviate CMRR. What that tells you is basically you can calculate this by doing the amplification of the differential mode divided by the amplification of the common mode. And you're probably like, what in the world is differential mode and what is common mode? And so common mode, when I think of it, common mode is equal to the noise, which is what you do not want getting amplified in your circuit. But differential mode is the signal, which is what you want getting amplified in your circuit. And so what I like to think about this is, let's say I have my radio playing in the background and I have another signal. So like I'm trying to talk into my computer And so I want my voice getting amplified. So that's the differential mode. And then that radio in the background, I don't want that getting recorded into this video. And so that would be like my common mode, because that's the noise. I don't want that interfering with my voice for the recording. And so that's a lot of times how you can differentiate the two. And so the amplification of the differential mode, that's usually what your gain was throughout the circuit. And so in our normal circuits here, the amplification we can see going back to the top here is our amplifications, our gain value. So what we got here for a gain, and we know our gains, the RF over RS most of the time. And so that's the amplification of the differential mode. And the amplification of the common mode should be very small in comparison to the amplification of the differential mode, because we don't want this signal getting amplified at all. So this should be a relatively small number speaking, where the other one, the amplification of the differential mode, should be a larger number. And so that's how we can do those two, so you know the difference between. And so I need to tell you guys, there is an equation you need to know. And so when you search up common mode, so let me show you guys, there's a specific equation that comes up, common mode rejection ratio equation. And so when you look the common mode rejection ratio, it will tell you oftentimes that the common mode rejection ratio is equal to the amplification of the differential mode over the amplification of the common mode. And then they have the common mode ratio, which they set equal to 20 log base 10 of the CMRR. And you're probably like, what in the world is this? Because the common mode basically ratio, that is measured in decibels. And so what we have to do is oftentimes for rejection ratio, we have that not in decibels, that's just in a normal number format, and we have to convert it to decibels, which is the logarithmic scale. So you can see here, we're going to have a logarithmic scale. So let me show you a common Bode plot, because Bode plots are very important. Bode plots. Okay, so usually they're in decibels. You can see here on the y-axis. So like this magnitude in decibels. So, you know, that's what happens a lot of the times. So you put it in the log scale. And so I'm going to show you guys here. So the common conversion is for our CMR, which is the common mode ratio, is going to be equal to 10 times the log of the power ratio, which we can say the power outputted divided by the power inputted. And we can also put in here, it's 10 times the log of the voltage outputted in squared. So let me just do the voltage output square divided by the voltage input squared. And so that's how we get our common mode ratio. And we can also set this equal to 10 times the log, and it's the amplification of the differential mode over the amplification of the common mode, which we can also write as 10 log, and that is our CR. And so that's how we can write it here. And that's converting it from basically the normal scale we use, which is like 1, 2, 3, 4, to the logarithmic scale, because the common mode ratio here is measured in decibels, which is in the logarithmic scale, and we're converting it. And so here what we do is, oh, sorry, I forgot to tell you guys, this 2 here, remember when you have an exponent for log rules, because log rules with exponents, it basically goes to the front. So you can see here, just to refresh your memory, when you have, see how, oh, let me get a better one. Let's see, right here, this logarithmic rule, look down here. See how this n, you can pop it to the front. and rewrite it as n log m. So what we're going to do here is we pop down this 2 here because it's squared to both terms, and we pop it to the front, and that gives us 20 and 20 here, and because 2 times 10. And so what we can do here is we can convert it from our common mode rejection ratio and convert it to the decibels for the common mode ratio. And so that's an important part of what common mode the ratio does. And so going now back to the rest of his, so we talked about all of those, we can look at a few examples. So give me just a question from the homework and we'll walk through it. And so someone just chat something in the chat box, which problem you want to see done. Anyone have any? I can just do some if you want to, but I feel like it'd be more beneficial. We do one that's confusing to y'all. You have any ideas, Jenna, Fady, or do you want me just do random ones? Or
Is that the one that's due on Tuesday?
Sure. Okay, which one?
Honestly, Annie, I didn't start on this yet. I was doing the book problem. So yeah, just
Okay.
choose the hardest looking one.
I'm just gonna start with number 1.
Wait, no, we already did those though. No,
Oh,
these were
wait, this
yeah.
one.
Yeah,
number 1 here, or do you want me to do number? Yeah, I'll just start with 1. Okay. Okay, so for number 1, design an inverting amplifier to provide a gain of 25 using practical components. And so an inverting amplifier, it looks something like, if we have our positive terminal here, our negative terminal, we know we're going to have feedback for this one. So we're going to have an RF here, and we're going to have an RS. And since it's inverting, that means the voltage source is hooked up to the negative terminal. And then we have, for the positive terminal here, it's hooked up to ground. And then we have our voltage output here. We have this as RF and this one as RS we label. And I label this as our V input. And so we can get the equation we know for a non-inverting amp, which is VO for output is equal to V in times negative RF over RS. And so if we want to gain, which is 25, then we know our gain is from this portion right here, RF over RS. So gain of 25 would be like 25K over 1K. You know, that can work. So what I'm going to do here is I'm going to set RS equal to 1K ohm, and I'm going to set RF equal to 25K ohm. And now that I know those for my ratio, let's look at number B, because that will give us the gain, because the gain is RF over RS, which is 25. If this amplifier is connected to a signal generator that produces 20 millivolts peak-to-peak sine wave at 1 kilohertz, what is the ideal output voltage? Okay, let's look at this. So for this part, I have 20 millivolts peak-to-peak sine wave. So right here, 20 millivolts, let's put, because this will be, remember how they said the generator is equal to what voltage you're basically putting into the circuit, what's getting generated in the circuit. So I can rewrite this instead of V in, I can always say VG here, and for the voltage generated. And so we had 20 millivolts peak to peak, and it's a sine wave, so we know. So I'm just going to write sine wave over here so I remember. And it says the frequency is, so frequency equals 1 kilohertz. We know the period is equal to 1 over the frequency. So if I do 1 over, so let me just type in here, 1 over 1000 for 1 kilohertz, I get 1 millisecond. And so since I get 1 millisecond here, I'm going to put for my period, I'm going to write that here. Period equals 1 millisecond. And now that I know that, I can draw sort of what this voltage generated looks like. Okay, so let me get both of my graphs here. So let me do the voltage on this one and the time on here. So I'm going to do my time in milliseconds for you guys. And we know the period is 1. So I'm just going to do it right here, 1, and then I'll have 2 here. And we have 20 millivolts peak to peak. So that means 10 millivolts up, 10 millivolts down. Oh, sorry. That's one. So 10 millivolts up, 10 millivolts down, 10 millivolts up, 10 millivolts down. Okay. Now that we know we have 10 millivolts here, and we have negative 10 millivolts here, because this is our voltage in millivolts. And we know this is the V generated graph. We know for the output is going to be equal to this 20 millivolts peak to peak times our gain, which we found was 25. So our negative, then 25 here. So if I do 20 times 25, I'm going to get negative 500 here. Sorry, times that negative as well. So negative 500 millivolts peak to peak. And it's going to be kept at the same frequency. Don't worry about frequency. It usually stays the same from input to output. So the frequency is going to remain 1 kilohertz at 1 millisecond. So since I have 500 millivolts peak to peak and there's a negative, that means it's inverted. So I'm going to go down. I'm just going to say this is negative 250 here, and this is 250 up here, just so I don't have to draw it super large. And it's inverted, so it starts negatively, then it goes positively, and then it goes negatively, and then positively. So this is my voltage output. So you can see that I had negative 500 millivolts, so peak to peak, because this 20 millivolts we had down here was peak to peak. And so it stays the same and just times the gain, which is 25. And that's how I got the value for my voltage output.
So
yeah.
Are you done with 1B for now?
And so I'm done with 1B.
Okay.
That's basically, this is the ideal output voltage, negative 500 millivolts. I just showed you through the illustration how you would illustrate it.
What did we need the frequency for? I mean, it sounds like the 20 millivolts.
Frequency tells you the period. So remember how I said frequency is 1 over.
But we didn't even use the period in the calculation. You just multiplied the 25.
Oh, I didn't use it at all in the calculation. I used it for graphing purposes, so I knew when one period of the sine wave occurred.
But I mean, do we even need to graph in order to solve B?
No, you do not need to graph. It's just good for visualization, because I like seeing visuals more than, so I know what's happening.
Okay, just making sure, because I mean, it looks like that once we got the 20 millivolts, that just our VI, and then we already have RF over RS from the one we designed. So
you're good. You don't need to draw it, but he will ask you to sketch it later on, so that's why.
Later. Oh, damn. All right, got it. Thank you, bro.
And then so now I'm going to go to part C here. So part C asks, most signal generators have 50 ohms source resistance. How will this affect the output voltage in your design? Okay, so if we have 50 ohms source resistance, we need to add a resistor here with the source. So our source is this VG. So I'm just going to add this source resistor here. And so I'm going to call this R source. R source is equal to 50 ohms. And so now that I know R source is equal to 50 ohms, okay, how will this affect the voltage in your design? Well, we know we're going to get input bias current through this chip here. And the input bias current, he knows, because remember when I told you guys, when you have input bias current, you're going to have to multiply it here by the source resistor. Because I knew we had a source resistor, I knew there must be input bias current coming into these terminals, because we're going to have to use this equation, and this is the only one that has a source resistor in it. And so we know here we're going to have to use the input bias current value, which is supplied by the data sheet. And for the data sheet, it says here for the input bias current at normal conditions, it is 80 nanoamps. And so since we know that the input bias current is 80 nanoamps, we go here to 1 be, up here. And what we do is we plug in our 80 nanoamps going through. So I'm going to just draw it here, say 80 nanoamps. And we know we can use the equation now, which was given here for a voltage output for DC airs. What we're going to have is we have our normal inverting amp. So we have an inverting amp. So this equation here will have to be modified for an inverting amp, but we'll use this one since we have a voltage generated. And we don't have a voltage offset, but we do have a source resistor, which will have an input bias current. So we have to use these two equations. But remember, these equations were for a non-inverting amp here. So we just have to adjust it. So the only difference, if you recall, between non-inverting and inverting is the inverting just has negative RF over RS instead of 1 plus RF over RS. And so you just have to modify the equations here. And so I got, just mark that out, put this in, and then do it same right here. You need to do that. And then let's plug it in. So let me write out the equation for you guys so it makes sense. So let me write it out. And what we're going to have is our voltage output is going to be equal to the voltage generated. So that's our 20 millivolts peak to peak times the negative RF divided by RS plus, and then we don't have any offset voltage, but we do have source resistance. And so we will have input bias current, so RF divided by RS, and then times IPRG minus IN, and then the parallel of the RS and the RF. And so let's plug in the values we're given right now. You know, voltage output is equal to, and the source generated is 20 millivolts peak to peak times negative RF, which is 25K ohms, divided by RS, which is, oh, sorry, right here, I should change that for an inverting amp. RS is going to be 1K ohm, and then plus, and then the gain, again, for a non-inverting amp would be the same thing, negative 25K ohm divided by 1K ohm, and then minus, or sorry, 1K ohm, and then multiplied by the input bias current, which we know is 80 nanoamps from the data sheet, times the source resistance, which here it's 50 ohms, and then minus the input bias current for the other one, and then the parallel combination of RS and RF, which is 1K ohm in parallel with 25K ohm. Now that we know that, we can solve. And when we solve this, let me do it just on quick calculator here. Let me see if I can copy this over.
So IP and I are the same number, correct? They're
what?
both IP.
Yeah, IP and IN are the same number because input bias current, if we're referencing the data sheet, unless he specifies, they are both 80 nanoamps.
Gotcha.
So V out, for V output here, I'm gonna just simplify this. So 20 millivolts, we know peak to peak, negative 25K over 1K, that would just be negative 25 plus, and then negative 25 here again, times 80 times 50, if we think that'd be 4,000 nanovolts. So 4,000 nanovolts, and then minus here, this would be 80 times this parallel combination of 1K times, okay, let me get out my calculator. Let me just do this, sorry. I need to find out the parallel resistance. But you would solve that and get your output voltage here. So let me do this right here. So 1 times 25 divided by 1 plus 25. I get this 0.9615. Oh, let me just do Desmo's scientific calculator. This is a really good one if you need a calculator during exams. So 20 e to the negative 3 for millivolts peak to peak times negative 25, and then plus negative 25, and then times 80 nanoamps, so 80 e to negative 9, and then times 50. Here's something to do. times 50. And then minus 80 e to negative 9. And then multiplied by 1k parallel with, so that'd be 1 times 25 divided by 1 plus 25 here. So if I look here, 20e to negative 3 peak to peak times that gain, which was negative 25 here, and then plus the gain, which is negative 25 times 80 nanoamps times 50 ohms for our resistor from this force, minus 80 nanoamps, and then times 1 times 25 divided by 1 plus 25. And then when I did that, let's see, oh, I just left a blank there. Try to find, oh. Looks like they don't like that. So let me see if I can do times 10 to the negative 9 instead of these. So times 10 to the negative 9. Then times 10 to the negative 3. And when I do that, I got negative 0.5001. So if we think about that, that is very close to this number. There's just a little error there due to the actual source resistance. So for our value, we got this. So I'm going to copy it over and I'm going to paste that in here. So for V out with RG, the source resistor, we got this value. So volts peak to peak. And so that's important to know.
So this is a more realistic
number. Yeah, of what it's going to give us.
Since every source technically does have like inner resistance.
Yes.
I see.
And so now that we know that, let's go to 1D. And so 1D, what's the maximum frequency your amplifier can faithfully reproduce? And so this one, I had to ask the tutor on because I didn't even know how to do this. And so
question, like, what the fuck does that even mean?
Yeah, he didn't go over this, but the maximum frequency is the gain bandwidth equation, and that's equal to, for my DAX, if you guys remember, it was 750 kilohertz. That's usually the typical value. And so we know here our gain was 25 in, so bandwidth equals 750 kilohertz divided by 25, since our gain was 25 in this equation. And this is just the typical value. Sorry, the 750 kilohertz is the typical value for the gain bandwidth product. And he went over that in the lab, but if you aren't in his lab section, you might not know that. And so that's the value we often have to use. So 750 divided by 25. If we think about that, when I do this here, when I do 750 divided by 25, so let me do, so 750 times 10 to the negative, times 10 to the 3, and then divide by 25, I get 30K. So when I know this bandwidth is going to be equal to, let me type it in here, bandwidth will equal to 30 kilohertz. And so that's what we get for the maximum frequency because it's divided by our gain. And so that's using the gain bandwidth product. Now for 1E, what is the maximum input voltage that your amplifier can faithfully reproduce? And so the maximum input voltage that your amplifier can faithfully reproduce, I'm thinking about that one again. How did I solve that one? Okay, the equation here. Oh, okay. So we know voltage output over voltage input, that's equal to our gain. So we know G, let me think about this. G, oh, G equals voltage output over voltage input, if you think about it. And so we know voltage output, if we think, what's the maximum input voltage that your amplifier can faithfully reproduce? So let me real quick pause and look at this. Sorry, I have to pull up just an equation, so give me a sec. Okay, and knowing that our maximum output voltage, if you recall, there's a specific, how I said the amplifier can only get to plus and minus of 1 volt of the voltage supplied. So the normal voltage supplied here is 15 volts, and to negative terminal, it's negative 15 volts. And so if we know our gain is 25, and we know the voltage output for the max would be positive 14 volts, or it could also be negative 14 volts, but divided by V, the input voltage. So if you solve for the input voltage here, what you're going to get is you're going to get 14 divided by 25, which is 0.56. So your maximum input voltage would be 0.56. So Vin equals 0.56 volts. Okay, hopefully that helps with question 1. And then
Bro, do you really think questions like 1E would be on an exam? Like, I feel like,
no, probably not.
yeah.
Okay.
Like, even when I see questions like these on the homework, I honestly like skip them because I'm like, this shit is a waste of time.
Yeah. And then which other, I can do just
I'll definitely do 5.
5. You want me to do part B? I don't have too much time, but I can do B.
Okay, let's do B.
Okay. Let me clear this and let's start. So for 5B, what we need to do, it says 1 volt peak to peak for voltage generated, and then we have 0 volts going into this op amp. So when I'm looking at this, I see, oh, okay, this right here, if we think about it, is close to a voltage follower. So I'm like, okay, V out equals V in. So I'm like, okay, this is just 1 volt peak to peak here, because this one's going to be so tiny. 50K times 80 nanoamps. Let me show you what the calculation, because we know input bias current is usually 50K times. So let me just show you how big that number would be, because it's irrelevant to the equation. So 50K and then times 80 nanoamps. So 80 times 9. That's 0.004. So you have 4 millivolts. However, your voltage supplied is 1 volt peak to peak. So 4 millivolts is so small in comparison to that. I'm just going to say 1 volt peak to peak is my output for this voltage follower. And so I know this will be 1 volt peak to peak, at 100 hertz. And then if I know that's going to be my voltage on this negative terminal here, I can redraw this so it makes more sense to you guys. So just ignore everything over here now, since we know what the output voltage was. And it's going to look like this, our 100 volt peak to peak at 100 hertz. And so now I have this configuration, and this reminds me of an inverting amp configuration. And if we know inverting amp, it's V out equals VI times negative RF over RS. And thinking about this, I'm like, okay, V out equals the V input, which we know is 1 volt peak to peak. So I'm going to write 1 volt peak to peak, and then times negative RF, which is negative 150K. So negative 150K, and then ohms divided by, and then RS is 10K ohms. Knowing that, this is negative 15 times 1 volt peak to peak. So this would be negative 15 volts peak to peak. And so now that I know the output voltage is negative 15 peak to peak, the frequency remains the same. So that's at 100 hertz. And so let me graph this now. So we know our original input was 1 volt peak to peak. So I'm going to draw the graph here. have voltage here, and I'm going to have my time here. And the period, we take 1 over 100 hertz. So 1 over 100, what does that give us? 1 divided by 100, I got 0.01. So I'm just going to label here like 0.01, and I'm going to have 0.02. And for this x-axis, it will be in seconds. And going over here, I know that now. Oh, oops, sorry. And now I can graph this since I know it's 1 volt peak to peak. So that's going to be half a volt up, and then half a volt down, then half a volt up, and half a volt down. And so this is going to be 0.5, and this is going to be negative 0.5. So 1 volt peak to peak, then times, let me see. Now that I know that, I know the input voltage, I'm going to have to graph the output voltage. So this right here, I'm going to keep it all as one color. So I'm going to say V input. And then for my output, I'm going to say the output is negative 15 volts peak to peak at 100 hertz. So that's going to be an invert, and it's going to go 7.5 down and 7.5 up for inverting. So I'm going to do that in purple here. And when you see what it looks like, negative 15, and then all the way up to 15, then negative 15, then all the way up to 15. So this will be our, sorry, to 7.5. And then this will be to negative 7.5 because it's peak to peak. So that means from this peak to this peak here, it should be 15. Okay, now that we covered all that, that should be our output versus our input. So I'm going to label this VO versus the V in. And so that's what your graph should be looking like. And that should cover everything. Hopefully that helped a little. And then I'll upload this for the others. But hopefully that helps out.
It really did. Thank you, bro.
Yeah, it helped a lot. Thank you.
See you guys on Tuesday. Bye.
Bye. Thank you.
See you.